In this video, we will see how to set up a co-simulation between a hydraulic system in Activate and a 3D mechanical model in MotionSolve. My name is Ronald and I'd like to show you how to prepare the multi-body model, how to prepare the Activate model, and how to perform a co-simulation of hydraulics plus multi-body. The principle of co-simulation on proceeding of modeling is always the same. With two partners who want to co-simulate, we have two possibilities to combine them. Either the first partner takes control of the whole co-simulation process or the second one does. That means in practice, with Activate in MotionSolve, the Activate model is called from inside MotionSolve, for example, as an FMU, or the MotionSolve model is called from inside Activate, for example, with the MotionSolve co-simulation block. Which direction is the right one for you depends on the simulation task and the focus of model development. In this video, I will focus on Activate and take MotionSolve in co-simulation as a submodel. As a simple example, I've chosen this lever, which is actuated by a hydraulic cylinder. The hydraulic system consists of a cylinder that is controlled by a switching valve. The cylinder should move to different positions. The position control is done by a 3-point controller. The variables that are typically exchanged and used for coupling are flow and potential variables of the specific domain. In mechanics, the flow variable is velocity, the potential variable is force. In our case study, I take the velocity from the mechanical part of the cylinder in MotionSolve and the force from the hydraulic part of the cylinder in Activate. Before we can start a co-simulation run, we have to prepare the models. Let's start with the MotionSolve model. The exchange variables velocity and force are created as solver variables. In order to make my life easier, I also add the position, respectively the displacement of the cylinder. As next step, I define the inputs and outputs of the MotionSolve model. Only these inputs and outputs later are visible from outside. Inputs are created as solver array with type plant input. Outputs are created as solver array with type plant output. Now we can assign the variables to the inputs and outputs. Input is only the force, outputs are displacement and velocity. The solver variables have up to now no connection to our system. Three things are necessary. We have to measure the displacement, we have to measure the velocity, and we have to apply the force. All this can be done using markers, MotionSolve functions and force elements, but my personal favorite is using a spring damper element. It directly delivers displacement and velocity and allows to apply a force. The spring damper is connected to rod and cylinder at top point of the rod and the bottom point of the cylinder. On the properties page, the stiffness K is set to expression. Now, the spring force can be defined by any expression, for example as a function of position and time. In our case, it is just the solver variable force. The damping C could be 0, but I like to set a small amount of damping. It's numerically easier to consider damping at mechanical side instead of at the hydraulical side. Measuring displacement and velocity is just as easy. Add the solver variable displacement, We define the expression as the length of the spring. This is directly the total length of our cylinder. There's one thing we have to consider. Activate uses SI units. MotionSolve can define any unit. In our case, lengths are defined in millimeters, velocities in millimeter per second. We can convert units either in MotionSolve or in Activate. I prefer MotionSolve. So, I add here the conversion factor from millimeter to meter. The definition of the velocity is similar. The expression is the velocity of the spring converted with a corresponding factor into meter per second. Now we are nearly finished with the model. As the icing on the cake, I like to model the end stops of the cylinder. It's an additional action-reaction force acting on the rod and cylinder like the spring damper element. Also, connecting points are the same. As property, I use a bstop function with displacement and velocity from spring damper. Minimum length of 450 mm, maximum length of 850 mm, a stiffness of 1 E8 Newton per millimeter, an exponent of 2, damping coefficient of 1 E5 Newton seconds per millimeter, and a penetration of 1 E-2 millimeter. But now we are finished with the model. As last step, we perform a simulation run to check our modifications. Everything okay. On Activate side, we start with a co-simulation block. We choose our mechanical model, either the MDL or XML file. The XML has the advantage that the simulation starts faster because the model does not need to be converted. Now we can see inputs and outputs in the dialog and also at the icon. As a quick check, I like to run the co-simulation without any connection, just with scopes added to the block outputs. I can see if the model works properly and get information about the initial values. In the next step, I connect both models to each other. Here it is necessary to convert a signal into a Modelica mechanical connection. For this purpose, we use a speed component from Modelica's mechanical library. It imposes a forced movement on the cylinder rod. For the other coupling direction, we still have to determine the hydraulic force. It can be done easily by inserting a force sensor. The measured force is directly fed back to the mechanical model. And that's almost all. I've chosen velocity as coupling variable. From numerical point of view, it's better than using the displacement. However, we must now specify the initial value of the position. Here it is easy. I can set it to 500 mm. Let's start the first simulation run. And now let's have a look to the results. Both pressure and position show an unstable behavior. We must exclude the possibility that this is a numerical effect. An unfortunate parameter is the filter frequency of the speed component. The exact treatment of the input signal doesn't work, and although we have a slow movement of our system, the filter frequency of 50 Hz is too low. I increase it up to 500 Hz and rerun the simulation. Now the results look much better. If you still have oscillations on your system, you can try to reduce the tolerance of the solver in MotionSolve. It's set to 0.01 by default. A value of 0.001 often works noticeably better. Now, the actual work with the model can begin, but that's your task. At the end of this video, I'd like to point you to two additional things. One is the PDF extended definitions. You can find it in the help of Activate, and it contains, among others, helpful information about co-simulation. The other is our forum. It's a great place for questions and knowledge exchange in all matters concerning Compose and Activate, but also for all other Altair tools. Thanks for watching and see you at the forum.